I think today we will talk on combustion instability. In chemical propellant rockets, namely combustion instability in solid, liquid and other types of rockets. But I thought in the last class we had not really finished hybrid. Therefore, let me, before coming to this topic, just spend a couple of minutes on the hybrid rockets. The very name hybrid means it is a combination of two phases, maybe a liquid and a solid, or a gas and a liquid and so on. But what is normally used in hybrid is maybe a liquid as an oxidizer and solid as a fuel. And we all know solid fuel is like polybutadiene, HTPB, PBAN and all that could be used. But essentially what is used is maybe a polybutadiene, and normally it is hydroxy terminated polybutadiene, which we used as a binder in solid propellant rockets. The liquid oxidizers which are used could be anything, could be liquid oxygen, could be, let's put it down, could be liquid oxygen, could be nitric acid, inhibited red fuming nitric acid, could be N2O4, and extra maybe we talked in terms of flocks. We had liquid oxygen which was in which fluorine was added to make it more powerful, and these are the liquid oxidizers, but mainly solid fuel is essentially polybutadiene, which is HTPB. How will the construction look like? You have a cylinder, a case, you have a nozzle, you have the solid fuel which is kept over here, could be any configuration. Let us take a star configuration or a circular configuration. I take a section over here, this is my solid fuel, and what is it I do? I spray the liquid oxidizer onto the fuel, and in case the liquid fuel, like let us say IRFNA, is hypergolic with respect to the fuel, then it begins to react at the surface, vapor is evolved, and I have vapor which keeps coming out, and here it is oxidizer rich, here it is the fuel vapor which is coming out, and therefore what is going to happen is here you have a stoichiometric mixture or a mixture between the oxidizer and the fuel vapor, it burns and then you get the thrust. This is the principle of hybrid, essentially somewhat in between a solid rocket and a liquid rocket. But in this case what happens is, provided the surface is hypergolic, the moment you inject it, chemical reactions begin to occur, the heat feedback to the surface generates the fuel vapor, say hydrocarbon vapor, and that hydrocarbon vapor mixes with the oxidizer and you get combustion taking place, and that is exhausted through the nozzle, and this is the principle of hybrid rockets, right. In case the surface is not hypergolic with respect to the oxidizer, then in that case I have to coat something on the surface which initially will start combustion by having a paste which is hypergolic with respect to the liquid oxidizer, heat gets generated, and once heat is getting generated, thereafter it is the heat transfer, namely the convective heat transfer, which evaporates the fuel, generates the fuel vapor, mixes and goes over here. Therefore the controlling thing in these hybrid rockets is essentially mixing. What is mixing? At the surface you have hydrocarbon vapors, mixes with the free stream of oxygen vapor, because when I inject it, this also due to the heat vaporizes, and therefore mixing is sort of a problematic. And what happened is, there was one person by name Dr. Dadiu in Germany, and what he suggested was, whenever we make hybrid rockets, since mixing is a problem, why not we put something like a turbulator. What is a turbulator? Let's again do, it's very common in all engineering situations, namely when I look at this particular thing, fuel is getting evaporated here, oxidizer is coming over here, I maybe make this constriction over here in the form of, let's say, petal, like petal is something like this. I put this configuration over here in this hole over here, and therefore this is, let's say, a turbulator, and what happens when the gas is flowing across it, it creates eddies and it helps to mix, and therefore we need something like a turbulator normally for mixing the gases, and so that combustion gets completed. Therefore, in the early stages, whenever people were working with hybrid, they never really used turbulator, they got very low performance. After using turbulator, somewhat mixing is better, but still the performance is not as good as in liquid propellant rockets, but it is better than solid fuel rockets. I think this is all about, but there is one distinct advantage in using hybrid rockets. What are the advantages? Let's say you have a solid fuel, and the solid fuel has a crack in it or some opening in it. Therefore, the surface area increases and you are spraying liquid oxidizer onto it. Because the surface area is increasing, the pressure gets generated. When pressure gets generated, automatically the pressure drop across injector is decreased because pressure here is higher, this is constant pressure, pressure gets decreased, and therefore the flow rate of oxidizer decreases, and therefore it is self-regulating. In other words, solid propellant rockets, if there is a crack, its surface area increases, pressure continues to increase. In the case of hybrid, if there is some surface defect, what happens is pressure gets generated. Once pressure gets generated, automatically the pressure difference between pressure at injection and pressure in the combustion chamber, now it is higher, increases, and therefore the flow rate decreases. If flow rate decreases, automatically the thrust decreases, and therefore I would say that the hybrid rocket is a little safer, and it can take certain surface defects. And it is these things which prompted more recently a person, a millionaire, a British millionaire by name Bert Rutan. He formed a company known as Scaled Composites, and he used hybrid rockets for ferrying people to space. Maybe he says space can be used for enthusiasts who are interested in looking. Therefore, he says it is something like a voyage or something like a place where you can go and view the earth from top, and therefore he used that White Knight aircraft which I showed you in the last time. In the belly of it he mounts a space capsule powered by a hybrid rocket, and this hybrid rocket takes him, the White Knight aircraft goes up to 15 kilometers height. From there he goes a little bit higher, maybe people are able to see the earth from top, and then it comes back to the earth, and therefore the purpose of the hybrid rocket there is for ferrying people from 14 kilometers to the ground back, and this is where the hybrid rocket is used. The company which does it is a private company known as, I think, Scaled Composites. Last week officially it was the launch pad was inaugurated in the desert in California. I think this is something which we can keep in mind. Therefore, I would say, well, hybrid rocket has not been very much used in practice. However, it is something like a convective heat transfer which vaporizes the propellant, mixes and burns. It has lower performance than liquid propellant rocket. However, it is safer than many of the other types of rockets because it is self-regulating, and it is finding increased applications. I do foresee much more applications for hybrid rockets in the years to come. I think this is all about hybrid rockets. We can even think in terms of other propellant, maybe flocks, if you want very high performance, maybe with metal embedded in the fuel, like maybe you could have some light metals. Let us say you have maybe magnesium, you have some lithium and other things, you could react it and generate more thrust. But what is generally used is, what is used by Rutan in his space capsule is N2O4 as oxidizer, and you have the HTPB as the fuel. I think this is all about hybrid rockets, but there is one problem with hybrid rockets. Because of the slow rate of reactions, it is very susceptible to combustion instability in the low frequency mode, and I am going to talk about it right away. We will talk, it is susceptible to low frequency combustion instability. Maybe since this is our next topic, maybe we will not spend some time at this point in time. Maybe after studying what causes combustion instability, it is new for all of us. Let us study this and then come back and see what is the real problem over here. Maybe with this I go to this new topic, a very fascinating topic of combustion instability. I wrote it earlier, maybe I write it again because we must be glued on to this topic. Maybe I will start with a very small example, and this example is not mine. This example was given in 1951 by one Professor Summerfield. He was at Princeton and he published a paper in 1951 in I think at that time AIA journal was not there, Journal of I think Rockets and Aircrafts or something like that. It was a journal which came much before AIA journal started coming, Journal of AIA started coming. You know, in this paper he gives an example. I modify the numbers because his numbers were in FPS system and not that easy to work on the board. Maybe I take a typical liquid propellant rockets, but as I say, I follow what Professor Summerfield did in his particular paper. He says, let's have a liquid propellant rocket. Let the mean chamber pressure be 5 MPa, 5 megapascal. 5 megapascal is something like chamber pressure is 50 bar. Let the fuel and oxidizer, both of them, be injected into the chamber at, let us say, P injected, and this value let it be 7.5 MPa. I just choose these numbers to illustrate some phenomenon. That means propellant is injected at a pressure of 75 atmospheres and the chamber pressure PC is equal to 5 MPa or 50 bar. Now what is it we are talking of? Let's put it down on the board. Well, we expect maybe pressure with respect to time, it's burning steadily. I expect the chamber pressure to be always 5 MPa, right? This is what I would get. You know, I start burning, it keeps on injecting propellant and something is leaving. And why do you get a chamber pressure? After all, you add some mass, let's say mass of propellant which is injected. And how do you calculate the mass of propellant which is injected? You inject something, that means you have injector orifices having total area A0. Let the CD value of the oxidizer and fuel orifices be the same, CD into A0 into under root of 2 rho into you have P injected minus P chamber. This is the rate at which mass is injected, right? So much kilograms per second. Okay, under steady conditions, and what we said is CD A0 2 into delta P by rho is the volume and multiplied by density CD A0, and this we must know all the time, right? And what is the rate at which gases are leaving m dot through the nozzle? It is leaving at the rate this we know terribly, PC into AT, right? This is the rate at which gases are leaving, so much kilograms per second. Therefore, we now say this is the value of AT, and the number of holes for the fuel and oxidizer, total number of area of injection is A0 all put together. Now I ask myself one question, you know, see so far what did we say? To get the equilibrium pressure, mass injected is equal to the mass which is leaving. But I have a strange problem. The fuel or propellant which is injected takes some time to burn. Suppose I inject a parcel of propellants at this rate here, it's going to start burning after some time because there has to be a delay. There has to be something like a combustion delay. Let me go back on that side again, because this point is important and this will be central to all our discussions. All what we are saying is there is a certain delay, because whenever I inject something, maybe I inject a liquid, it breaks into droplets, maybe fuel breaks into droplets, then it evaporates, the fuel and vapor mix together, then they react, and then out comes the burning gases. That means this we said occupies quite a tremendous amount of time. The vaporization takes time, atomization is fast, reaction may be fast, mixing before that also takes some time. Therefore, if I say the entire process of from injection to burning takes a time of, let us say, T delay, T due to combustion delay is Tc seconds, then I need to make some changes in this equation. What is it I am telling? Something is entering, it has to form gases before it leaves the nozzle, and therefore if I were to write an equation which takes care of the rate of mass variations, what is it I would be writing? I would be writing under normal circumstances dm by dt, the rate at which mass is getting accumulated in the chamber, is equal to CD A0 under root 2 into density into P injected minus PC is the thing which is coming in, and what is going out? Minus 1 over C star into PC into AT over here. But now I say this equation may not be really correct. Why? Because what comes out can happen only Tc later, or rather I must say the quantity which comes here is equal to T minus Tc is what goes out at time t. This is the equation, let us say dm by dt, mass at time t, this leaves at time t, but what should really burn is what is injected Tc time earlier. Therefore this is my dynamical equation, or this is my actual equation, and to solve this equation is difficult. But we must have a procedure, and that is what we will be doing in this hour. But therefore we find that there is a time delay before something happens, and therefore let us get back to this example. With this background, let us come back to this example again. What is it we are saying? Mass is injected, therefore initially let us say chamber pressure is 5 bar, and therefore I can now write the mass which is injected is equal to, again I write CD A0 under root 2 rho into, now I just put the units because after all it will be a constant. I have some chamber pressure I say is 5, injection pressure, that means 7.5 minus 5 is the value, or rather I say it is equal to K, I take all the constant outside, root of 2.5 is the mass of injected. I take all these constants K, maybe I have to multiply by 10 to the power 6 over here, all those things I take constant, put it into the K value. Now therefore beneath it I therefore now plot the rate at which I am injecting the liquid in this, and what is the rate I am injecting liquid? I say this is my nominal value, I call it as m dot of propellant which is getting injected, nominal value is what I am injecting, and I keep on injecting, and this is the value I am injecting, m dot p. Let at this particular instant of time t0, let the chamber pressure drop by let us say 0.5, that means this magnitude is 0.5, something happens in the chamber, maybe there is some problem with the injector or something happens within this chamber, and therefore what is happening is I am now allowing the pressure to fall from 5 to 4.5, so instantaneously it falls. Let us just assume something like this happens. Therefore now my chamber pressure, which is PC, now becomes 4.5 MPa. If it is 4.5 MPa, my mass which is injected is going to be K times, now 7.5 minus 4.5, which is 3 under root 3. Therefore if I were to put it in terms of the steady value of MP dot, which was the steady value, it is going to be MP dot into under root 3 divided by 2.5, which is equal to something like 1.2 times under root MP dot, which is equal to 1.1 times the value of MP dot, which is the nominal value at a steady. That means all of a sudden I am injecting little more, which is now 1.1 times m dot p over here. See, the pressure has fallen, because of that the quantity which is injected has now gone up by 1.1 times. It takes a certain delay, let me enlarge it, say it takes Tc time to evaporate, mix and burn together, and when it mixes and burns, what is the chamber pressure I get? Originally I had, when the nominal value was m dot p, I had the chamber pressure which was given by 1 by C star into Pc into At, and now I get a value which is 1.1 times, and therefore my chamber pressure will be equal to 1.1 times the value which was 5 earlier, which means after this delay time it continues at this value. After this delay time it increases to 1.1 into 5, which is 5.5 MPa. In other words, after this value of Tc, let us now put it together, the pressure will now increase to 5.5. What is now the implication? The implication is, maybe at this point in time when I said the chamber pressure is 5.5, the mass which is injected is now going to be the value of K into under root, the supply pressure is still 7.5 minus 5.5, that is equal to K root 2, and therefore if the mass injected is now K root 2, the value of mass injected in terms of the nominal value, which was mp dot, which was based on the difference of 2.5, is now equal to mp dot into under root 2 by 2.5, which is equal to 0.8 under root of mp dot, or rather this is equal to 0.999781 of the old value mp dot, which is the nominal value. And therefore what is going to happen when the pressure increases, the mass flow rate now drops to a value 0.9 of the old value corresponding to mp dot over here. Now what happens? Now it has come back to 0.9, and therefore this continues. This liquid evaporates, burns over a time Tc. Until it burns, nothing really happens, and when this quantity burns over here, the chamber pressure is now, I get mass which is injected is 0.9, the vapor which is formed or the gases which is formed is 0.9, and therefore 0.9 into the value of 5 will be 4.5, the chamber pressure now drops to 4.5 again. And this sequence, now again it is 4.5, again after a delay time it increases, goes over here, and so on. This fellow also goes to 1.1 again, from 1.1 it falls to 1, and this delay is Tc, and therefore you find that a momentary drop of 0.5 makes the chamber pressure oscillate between a value from 4.5 to 5.5 to 4.5 to 5.5, and out of a steady situation, when you have this delay term, what did you do? You started getting oscillations. Well, the oscillations are neutral in that maybe it keeps fluctuating between a value of, let us say, 4.5 to 5.5, whereas the nominal value before the test, before when it falls down, was 5 MPa. Is the process clear? I think if this is clear, I think we would have understood some part of combustion instability, namely a drop in chamber pressure whenever there is a delay causes this problem. I will come back to it. Let me give a physical example before I proceed with this, because we are talking of something like combustion and all that. You know, we would have seen many toys in the market. I just brought one such toy here. Let me get back and show you this, because it is very illustrative of the phenomenon. You know, you have these toys which are available in the market, and what you do is you just take this toy, you bend it once, it will keep on oscillating up and down. Maybe I put it on the table, I push it here, it goes, it keeps on rollicking up and down. It's in a state of neutral oscillations. Why does it have to do this? Let us take a look at what is the construction of this particular one. There are various ones. Maybe there is a small marble here, that is what is making this particular noise. Let's say I shift it. When I shift it, there is a sling and a marble over here. When I shift it here, the marble comes and hits over here, and the hitting is much before it has bent over here, and therefore this fellow comes and hits here and gives a force to this, but when it hits, it rebounds back, and even before it could come here, it comes here, rebounds here. That means there is a delay between the forcing function and the motion there is a time delay, and it is this time delay which keeps this oscillating once, and once you oscillate it keeps on going. This particular toy is different from a toy in which at the bottom you have a mass. Sometimes because of center of gravity you do, but in this case there is a marble inside, and it is this which keeps it going up and down, and the friction essentially stops it, and it is exactly the same thing what is happening here. You inject propellants, there is a time delay, the time delay precedes whatever be the change which happens, and this is what happens in the case of one case of instability, right. Can I say this is understood? If this is understood, let me go back to the next example. I just do once more and then I will say we can generalize it. Let us now assume that now I have another chamber, another rocket chamber, in which my injection pressure chamber pressure is still the same thing. I keep it at let us say 5 megapascal. Let me reduce the injection pressure to 7 MPa and ask myself what is going to happen in this case. Now I don't need to repeat much. All what I want to do is maybe make these two plots, maybe the chamber pressure as a function of time, maybe the mass which is getting injected as a function of time. The initial pressure is let us say 5 MPa, and maybe at time t0 we reduce the chamber pressure like in the previous example. I reduce the value to 4.5, that means I decrease it by 0.5 to 4.5. Now what is going to happen in this case? What is going to be the change? Let us say corresponding to 5 MPa I have a steady value corresponding to m dot p, which is steady. Now I have reduced it, the chamber pressure, from 0.5 to 4.5, and therefore I use this space to work out. Now I say m dot, which is now injected, m dot p is going to be the value of k under steady conditions, it is equal to k root 2, and now this is the steady value. When the chamber pressure has got reduced to 4.5, what is going to happen is it is going to become k into 7 minus 4.5, that is equal to k into under root 1.25, no 2.5, or rather the new value of mp dot is going to be under root of 2.5 by 2, which is original, which is equal to under root of 1.25, and therefore this under root of 1.25, 1.21 will be something like 1.12, and therefore now I find that at this point t0 it increases to 1.12 of the value of mp dot. And what is the repercussion? Well, it is going to burn, it is going to take some Tc time to burn, and once it gets combusted, all the delay is over, then at that point of time the pressure increases. What will be the value of pressure? It is 5, that is the new value of pressure will be the value of 5 into 1.22, which is equal to something like, instead of having I am sorry, it is 1.12, 11 11s are 121, and therefore it is 1.12 over here, and therefore this is going to give me 5.6 MPa. Therefore the pressure now goes up to 5.6 MPa, and when it is 5.6 MPa, well, the mass flow rate now decreases and it becomes equal to, with respect to the steady difference of 2, now it is going to be 7 minus 5.6 divided by 2 over here, that is equal to under root of 0.7 1.4 divided by 2.7, the value is 1.12, then it has burnt over here. When it has burnt over here, after this maybe I have a delay time during which it comes, the pressure now comes to 4.2, and then after 4.2 it goes still further, and therefore it could even diverge, it could keep on increasing the value, and here if I were to put it down, it is 0.84, this value 0.7 is 0.84, and from 0.84 it picks up and goes to 1.18, and then it comes still further and it keeps increasing, and therefore even the oscillations need not be neutral, it could keep on increasing depending on this pressure difference. I do a third problem in which I choose this value as maybe 9 MPa, this as 5 MPa, and what I get for this pressure, which I do not need to do at this point in time, is maybe I again start with pressure of 5 with respect to time, I drop it from 5 to 4.5, then in that case what happens is it goes like this, it goes like this, it goes like this, maybe it does not go all the time, it keeps decreasing and it comes back to the neutral. In other words, why did it happen? Because I had much higher flow rate compared to this, and I do the same sequence, I can trace that the pressure with respect to time follows a decreasing trend. And let me put the numbers through because we should not go too fast also. 4.5, the value goes to 5.3, the value comes back to 4.8, and so on, it will be something like 5.1 and so on till it comes back to this. Therefore, what we have just done is we have taken a simple case wherein we varied the injection pressure, kept the chamber pressure constant, and we found either the oscillations are so formed that it keeps on oscillating in a limit cycle mode, the same amplitude, or else we started with this, therefore let us start with this again. It could either go and diverge out like this and ultimately explode, or I could start like this and it keeps decreasing with time and it reaches this. Either it could be neutral, it could diverge, it could keep on increasing, just like you have equilibrium, because this is neutral, this is diverging, this is something like a decaying oscillations or a stable system. It is possible to imagine all these things in this. And the example which I say is very similar to what we are saying, keeps on oscillating. Now let us try to understand this a little bit more, because I think it should be possible for us to write an equation. And what is the equation we had? This was the equation. Can we solve this equation and get some inferences? Because if I were to do it mechanically, if I were to do all these things maybe with 5, 7, 5, 7.5, maybe 5, 9 and all that, I will find a system, or I will find an equation like maybe when I have P injected minus the value of chamber pressure divided by Pc, if it is equal to half, I get neutral oscillations, provided I do a lot of trials. If it is going to be less than half, I get the case wherein I get diverging oscillations, and if it is greater, or if it is greater than half, then I get a stable system wherein it comes like this, maybe keeps decreasing and falls back to 0. It is possible to do it numerically. Let us try to solve the equation. After all, we know how to solve a differential equation. Let us try to solve this equation. But as I told you, solving is not going to be straightforward. I have mass generated Tc earlier is what leaves the nozzle. How do I do this? Now we must recognize one or two small things as a precedent before I solve this equation. See, when I say combustion time delay Tc, let us say it is equal to 500 milliseconds. I just choose a number, a large number. See, in a large rocket 500 millisecond may be different than in a small rocket. Therefore, I must say I must compare the delay time or the time taken for reactions to occur with respect to something else. What is that other time scale? which I should have in mind. Like for instance, let's take what are the other times which could probably enter into our system or into our computations. Let's say, what is the residence time? What is the time over which a propellant stays in the chamber, propellant vapor stays in the chamber? What is the time which is available for the propellant to stay in the chamber? Maybe I inject something here, I form gases here, m dot g, the m dot g stays in the chamber for some time before it is evicted. We said maybe L star is equal to Vc by AT gives us the time over which a propellant, if the length is large, the gases are going to stay for a longer time, maybe the chamber may require, it can still accommodate a large value of Tc before it becomes unstable. Why is it I am telling this? Maybe I should go back to that problem again and ask you one more question. If Tc was 0, let us say if Tc is equal to 0, would you have got that phenomenon? And if you are going to get that phenomenon, why? If you do not get that phenomenon, why? Let's try to imagine this again. Let me say, yes, my chamber pressure with respect to time, originally I had 5 bar, it drops to 4.5 bar, but there is no time delay, immediately it burns and immediately it goes out. What is going to happen? It goes back here and adjusts, goes back here, adjusts. Therefore, without a time delay, I cannot think in terms of these oscillations. And what is the role of this time delay? Well, the same thing, there is a lag and that is what causes it. Now, can I compare the time delay with respect to some other time here? Because if I have a very large chamber, maybe my time delay, which is still maybe the same value, I can still accommodate it and it may not give me that problem. Therefore, I define something known as residence time, which is the time which the propellant stays in the chamber. And how do I define residence time? Maybe the rate at which gases are generated in the chamber divided by volume of chamber. If I now put it down, it is meter cube by second divided by meter cube. No, it must be 1 over T residence, right? Or rather, I now write T residence is equal to Vc by Q dot, the rate at which mass is getting generated in the chamber divided by the volume of chamber is the time the gases spend in the chamber. I want to express this. How do I write this equation down? Let's put it down. T residence, volume of the chamber, by volume of the chamber I mean this is the volume over here, into mass of the gases in the chamber divided by the density. Now, can I write an expression for m dot g, what is generated? Whatever is generated goes out through the nozzle, 1 over C star into PCAT. Therefore, I can still write T residence as equal to Vc, what is rho g? PV is equal to MRT, M by V is density, therefore rho is equal to PC by RTC divided by mg, C star comes upstairs, so over here, PCAT over here, and therefore now I can cancel the PC out, it is not a function of chamber pressure anymore, and therefore I get Vc by AT we have defined as L star, anyway we know its residence time, into C star divided by RTC. And do you remember what is RTC equal to in terms of C star? We have done it earlier. We said C star is equal to, yes. See, some of these things are, we must keep on our fingertips so that we can relate it. We said C star is equal to under root RTC by capital gamma. Therefore, we get RTC is equal to gamma square into C star square. Substitute the value of RTC there, we get T residence is therefore equal to L star C star by gamma square C star square goes off, and the value of T residence is therefore equal to residence time T of the gases in the chamber is therefore equal to, I just get L star by gamma square, you know gamma is a function of small gamma, into C star. Well, it makes sense, L star has units of meter, gamma has no units, meter per second, this is second, and this is your value of residence time. You are able to get the residence time, and now I will say my Tc, that is the combustion delay, should have something to do with this residence time, and therefore I would like to bring in the residence time and combustion time into this equation. Combustion time is already there, only thing I do not know how to solve this. Therefore let us try to solve it in some way, let us try to put some things down and try to solve it. We will first try to bring down or bring in the value of residence time, and therefore let me first take a look at this particular thing, the mass which is leaving the nozzle, and before that let us try to find out what is the variation in chamber pressure. We say m is equal to PV by RT, we keep doing the same thing, you know, PVC by TC is the mass in the chamber. We assume TC is constant because small changes in pressure or oscillations is not going to change this substantially. Therefore let us simplify this equation in terms of dP. We get dP in the chamber divided by dt is equal to RTC by Vc into under root 2 into density P injected minus Pc minus, I write the value again, RTC by Vc into 1 over C star into PCAT. This should be multiplied by CD into the area of orifices A0, CD A0. Essentially what is it we are looking at? We are looking at the variation of Pc with time. We are trying to see whatever we studied just now with numerical example, we found under some conditions it goes like this. What is the rate at which pressure changes with respect to time is what we want to predict using this equation, and precisely that is what I am solving for. Therefore, but we also note something here, I must not forget that, which is very primary. This happens T minus Tc before this, therefore this is as a function of time. Therefore Pc is also at time t over there. Let us simplify this part of the equation, let us get this out in terms of maybe residence time. Let me go back here. Precisely what did I write? RTC was equal to gamma square C star square, Vc by At is L star into, I still get a value of C star into Pc over here, and therefore the second expression over here I can write it as equal to Pc into L star divided by gamma square C star, and this is equal to residence time, and therefore the last part of this gives me a value Pc by T residence. I still need to solve this, I do not know how to do this. Let us see how I can manipulate this in some way, and this is quite interesting, quite simple. Well, let me say the chamber pressure at any instant of time Pc, at any instant of time is denoted by Pc, which is equal to the steady value. In our example the steady value was 5 MPa plus I have P prime, some oscillation, some disturbance in it. Therefore I can write this expression now as RTC by Vc into under root of 2 rho into P injected minus the value of Pc, that is a steady value, minus the value of P prime, or rather I take the steady value outside, I take it as RTC by Vc into the steady value, that is 2 rho into P injected minus the value of Pc bar over here, and then I write the balance as 1 minus P prime divided by, I have to divide it over here, P injected minus PC bar to the power half. All what I have done is I have taken this outside, I took this again outside, and therefore I have P bar minus this over here. I also know that the magnitude of P prime may not be very large, and therefore P prime divided by this may be a small number, and therefore I can write this part of the expression as 1 minus P bar divided by maybe 1 by 2 of P injected, P injector, that is the injection pressure, minus the value of PC bar over here. And what is the value I get over here? Let us see, RTC by VC, we have just now seen what it is, and what is the value of this 2 rho into PC, somewhere we dropped the value of CD. Where was CD? We should have got mass which is going CDA0 here, that means I should have had here CDA0. Why did we drop this? We should have carried it forward, and if I take the value of CD A0 into 2 rho is the regular mass which is leaving through the nozzle, because under steady state conditions, what is it I get? I get RTC by VC into CDA0 into this is the value which is steadily going, that is 1 over C star into PC bar into AT, steady value of pressure, mind you, please be clear about it, into I write the same equation here, 1 minus the value of half of P prime divided by the value of P injected minus the value of PC bar. Does this make sense? You have a steady value of thing which is getting injected, and under steady conditions whatever is getting injected is leaving through the nozzle, that means 1 over C star PAT, and therefore I take RTC VC, which was the coefficient, 1 over C star into PCAT, and if I were to look at this value, I again substitute RTC is equal to gamma square into C star square, and I get the value of VC by AT, which is L star over here, and I get the value of C star over here. And what is it now I am getting? Let us again be very clear. What is it I have got? C star L star by gamma squared C, that is 1 over residence time, and therefore this expression now becomes PC bar by the value of T residence, and therefore what becomes of my equation? My equation gets terribly simplified, and now I am able to write this equation as dPC by dt as equal to, let us put that down, I get the value of P bar by T residence into 1 minus half of, I get the value over here as the pressure perturbation divided by this 1 minus half into pressure perturbation divided by the pressure of injection minus the steady value over here, minus the value corresponding to the last term, which we call it as PC by T residence. Therefore, you see I am able to simplify the equation quite a bit over here, and now what is it I have to do to solve this equation? To solve this equation, I need to get some way of relating the value of Tc, but mind you, something which we forgot, and what we forgot was this is at time T minus Tc. I need to make some changes in order to understand this, and therefore now I say we have already told, well, Pc at any time is equal to Pc bar plus the value of P prime, and therefore if I were to change, Pc bar does not change, I can write this equation as dP prime by dt as equal to the value of Pc, that is chamber pressure steady, divided by T residence into, I get the value 1 minus. If I were to make a manipulation and divide the numerator by Pc bar and denominator by Pc bar, I can write this thing within brackets as maybe P prime by Pc bar divided by P injected minus Pc bar divided by Pc bar, and this is the magnitude of the perturbation above the mean. I denote it by something like, let us say, if I were to look at this, I am looking at P bar by Pc bar, maybe let us denote it by a value, let us say phi or something, and this value, which again has a value 2 at the bottom, I say the value of Pc divided by 2 of P injected nominal value, this is what I divided, P injected minus Pc bar I denote by the value beta. I can write this equation as 1 minus the value of beta, which is just the value all steady values, phi denotes the perturbation, and there is I say it is phi of T minus Tc is what I get here, minus the value of Pc divided by T residence, and this is my final form of this equation. I dropped half because I brought half here because this value was small, and this is my final form of this equation. I just need to solve this equation to be able to get the value of how the pressure changes, and this maybe I will do in the next class what we will have, right. Therefore, what did we do in this class? We just told ourselves the moment fuel gets injected and it takes a certain time delay to burn, then there is a problem that maybe any change in pressure could get magnified, and for some values of P injected minus the value of Pc with respect to Pc, and that is what we are trying to do through this particular equation. We will illustrate the solution of this equation and then move forward in the next class, right. Well, thank you then.